just fair warning. So,
disregard what I just said. There's a second.
Just fair warning. We are recording now.
Oh my God.
It's not a camera. It's only a screenshot.
Why is the arrow
Camera's
blinking?
over there. Because it's recording. It's like taking a screenshot. How did you even notice yesterday? All right, let's get started.
He's awesome.
The cursor is really good. All right. Hey.
But really.
All right. Yesterday, we started talking about where electrons are in our quantum mechanical model, or Schrodinger's model of the atom. The only problem is, can we really tell where electrons are? No. So really, what are we looking at? Where they were, or a guess where they most likely are going to be, where there is a high probability of finding them. And we said that we use this idea of quantum numbers to identify these most likely spots where electrons are going to show up around the atom.
But why can't we know where an electron is? It confused.
Sam, like we talked about the other day, that in the process of us measuring where an electron is, we move it. So we can tell where it was when we were measuring it, but not necessarily where it is now.
So we don't know where an electron is, like, right now.
Correct. Right?
Okay.
Just like yesterday when we were looking at the Ohio map, right? We don't know where any specific person is now, but we have areas where we are highly likely to find them.
Okay.
Does that make sense?
Yeah.
Okay. Nelson, go ahead.
So when you say the quantum number,
Yep.
it's kind of like in this where like they don't want it to n equals 1.
Yes. So actually, let me do this. November 15th. Oh, that was expensive. I don't like physics. Don't worry, it's not for you guys. Don't worry about it. You don't have to worry.
What's 400.5 and 491 at?
Is this a point effect? I don't really get the whole ratio.
Let's go.
I'm glad this is being recorded.
Yeah. We just
Now it's out there for everybody to see.
Oh no.
Yeah. I really thought it. What'd you say?
That was a total like waste.
Okay. Alright.
I have to go on.
You gotta watch this now. Okay. Yesterday, we drew this picture, right, of the atom.
Oh no.
Okay.
Yes. Stop.
Where we had an XY axis representing the space around the nucleus, the origin representing the nucleus. And then, first thing we drew was a little red circle that kind of looked like this, right? That looks somewhat familiar. Okay. And then, I think we drew a green circle next,
With the little ears.
right? And it had like little ears on it. But we said, really, that the little ears were part of like this big figure 8 that sort of went like this.
Why is your figure eight?
Yeah.
Hold on. And then we had a blue circle that was outside of it, okay, also with little ears, okay, but once again, actually, let me do this. I know this is changing the drawing. Oh, I know this is changing the drawing from what it looked like yesterday, but let me draw the ears now like this, okay. Once again.
It looks like an airplane.
All right. So we had this picture up on the board yesterday. And we said that each one of these drawings represents, each one of these drawings represents a sublevel. I was going to go more general with a possible location or a likely location for electrons, but each one of these drawings represents sublevels. Okay? So we started off with the principal quantum number, and that was the one that symbolized like the big areas around the nucleus, right? We said that the principal quantum number or the principal energy level, kind of same sort of thing, were like kind of like Bohr's rungs on his ladder. Yes, here, big area, big area, big area where we can find electrons. But the thing that changed was Bohr's rungs on his ladder are rigid. You have to be here or here or here or here. But is that the case in here? No. That's where our discussion shifted to this idea of sublevels. That even within areas of high density, we find areas that are more populated than other areas. And the thing we talked about yesterday was with like the Ohio map, right? Within the area of Cleveland, we have those areas that are darker, those like Lakewood areas, right? And then some other areas that aren't quite as dark, like Westlake-ish. Does that make sense? Okay. All right. What we find out is that those areas of higher density start taking on certain shapes. I think we got to this yesterday, is that correct? Yeah, good. That some of these shapes are spherical, some of them are figure eight-ish, some of them kind of look like a crisscross, and then there's other ones like the F orbitals that are real complex and we won't worry about what they look like. So, and that's when we start looking at these sublevels, okay, they start showing up in a sequential order. The first sublevel in each principal energy level, PEL, so not what I wanted to do. Thought I was highlighting, but apparently not. PEL being principal energy level. So the first sublevel in principal energy level, when you go and watch it at home, it'll show up. The first sublevel in each principal energy level is called an S, and those are the spherical ones. If you look back at this picture, right, every time I change color, what's the first thing that I drew? A circle, okay, because that's the first one. The first energy level, or the first sublevel with an energy level is always a circle. Now, in the first energy level, is there anything else besides that circle? No. We talked about that when we get real close to the nucleus, are there a lot of electrons in that space? No, because what are all those electrons trying to do to each other? Well, trying to repel. And that's generally why we end up with this situation here. Okay? Good with that? Kind of is okay at this point in time. Then, once we get to the second level, the second energy level, we introduce the P sublevel. If you look back, right, what do the P sublevels look like? They look like figure eights. If we go back to our picture, right, here and here, right, what is the green part that I drew in here? It's a P sublevel, okay? The figure eight is the sublevel. But notice, what color is it? It's green, just like the circle that I drew. So this is all level 2, but this is the 2S level, and this is the P level. Okay? Does that make sense?
You might want to donate to people.
Okay. This being, oh, not what I wanted to do. This being the 2S level, right? And this being the 2P level. Because, Allison, what shape is it? Okay, so, Allison, what we're talking, okay, at the end of the period, I think we did this, right? Let's say we have an electron right there. Okay? And if we start putting quantum numbers on it, if we start putting an address on it, what is this electron's principal quantum number? 2. So its n is equal to 2. Okay? But if I have an electron that's in this space right here, okay, its principal energy level is still what? It's still 2. These electrons live in the same city. Okay? But were you guys, was it your class that was the other day when all 4 of them went by?
No.
Maybe it was 11th period. Maybe it was 5th, 6th.
Sounds like a.
What, the other day in 5th, 6th period, like 2 fire trucks and 2 ambulances went by like in the span of like 2 minutes. Like they were all going to the same. Yeah, that's not good. So, okay, here's go ahead.
So the 2 is for what we call it like the second rate.
Right.
And then the P is just because of the figure 8.
Right.
And then so if it was like the blue one, it'd be like 3.
Yeah. Let's do that in a second. Yes, let's do that in just a second. Let me finish this real quick and then we'll do questions. So, this one, because it's in the sphere part, right, it's in an S sublevel. So its L value, we assigned it as 0, because it starts at 0, okay? But then here, this electron, right, it's in a P sublevel, so its L equals 1. Does that make sense? Okay. If we go back here to this, right, because it's in a figure 8, right? It's in that figure 8 shape. I'll give it a second. Hold on just a second. Okay. So anytime it's in the figure 8 shape, right, the p orbital, not what I wanted to do. Wow. The p orbital always gets the L equals 1 value, regardless of where it is, big picture-wise. Okay? Let me do 2 more things, and then we'll go. So, this electron. Okay? Okay, so n equals 3, because now we've moved up a principal energy level. But what shape orbital is it still in? It's still an s orbital, so that means that L equals what?
0.
L equals 0. Okay?
What do you mean by it's still in S?
S is the spherical section. And Alex, there's always a spherical section in every level that we go up. The first thing we encounter is a spherical sort of section. Okay? I don't know. Yeah, I don't. Those aren't. That's not. S isn't sphere because it's a sphere. I'm not sure why they assign those numbers. Then this one, this electron up here, right? N still equals 3, right, Allison? But what shape orbital is it in? It's in a p orbital, so that means that L is equal to 1. Okay? These two electrons, they live in the same city. N equals 3. But they live on different streets in that city. Does that make sense? Yeah. Okay? These two, they live in the same city. It's a different city, but they live in the same city. But once again, they live on different streets. Okay? Good there? Good. L stands for the angular momentum quantum number. Okay? That basically tells you what sublevel it's in. Okay, that's. No, that's like another. So, okay, when we go here, what we find out is that just outside of this, okay, there is one that looks kind of like an X shape. Does that make sense? Okay. But these four are all the same orbital, which is kind of weird, and that's why it starts getting pretty complex. So
like the N orbital.
if I have an electron right here, okay, N is still equal to 3 because it's still in the third energy level. But now, because it's in a d orbital, L is equal to 2. It's still the same city as the other two orbitals, but now it's on a different street. Okay? Charlie, go ahead.
So which shape, like, which ones are the sub-levels?
The sublevels are SPD.
So
Okay?
they're like the figure 8, the
Right.
X, and the whatever.
Right. So in the first main level, the first principal level,
Okay.
there is only an S sublevel because how big is that first principal energy level? It's small. There's not very many places for that electron to live. Okay? When you get out to the second principal energy level, what's green on my picture, now there's a couple more places where that electron can live. Now there's two sublevels. When we start getting to the third energy level, now there's three sublevels, S, P, and D.
So is,
And the D are the crosses, yeah.
so N is basically the sub-levels.
Not N, L is the sublevel.
Where are the crosses? We don't see D yet.
Okay. This is going to get kind of messy.
How is it not messy?
If you know...
Yeah, how is this not messy?
Alright, relax. Allison, I'll be happy with D if you know that it kind of looks like this. That it kind of looks like it's an X shape. Right? That would be fine. Alright? Don't necessarily worry about where it shows up on this because it gets really messy.
And for like the test, we just like know.
If you know what those shapes, well, if you know SP and then D is kind of like an X shape, that's fine.
How is that one D?
Because Kennedy, this, this, and this are all actually the same street.
Can you give an example of D?
No, don't worry about it.
Oh, so we don't even like,
Well, you know that it's there, right? But it's an X shape, okay?
of what? Like another
It's
figure
another
eight?
place where electrons can live.
Like they're all connected.
Right. Yeah.
X shape, like the.
Yeah. Well, yeah. This was
It'd
kind
be
of
like
cross.
it'd be like two bands, like
Yes.
and around the whole
Yes.
thing. Got it.
Here, go ahead.
Wait, so is the red
Oh.
circle S?
The red circle is S, but it's specifically one S.
The screen's S.
The green circle is 2S
Oh, I didn't know that.
because there's multiple S's, like I said here, right? All principal energy levels have an S sublevel. Okay? If we talk about the sublevel being the street, every city in America has like main streets, right? And on Main Street, you have like the post office and the police station, right? Grocery store, things like that, right? Here in Westlake, we have a main street, right? It's probably Detroit, okay? Yeah, I mean, pick your pick, right? Hilliard's probably not Main Street because there's really not much on Hilliard, except City Hall, I guess. That's kind of school. But there's no like stores or anything on Hilliard, you know what I'm saying? It's not the best analogy in the world, but do you get the idea that like the S level is like Main Street, okay? Then the P level, now we start adding like side streets, okay? Like this is like the next biggest level. So like the equivalent here in Westlake would be like maybe this is like Crocker, Dover, Columbia, Clay. Does that make sense?
Wait,
Okay.
so is S the most populated, then it's P?
S always gets populated first
And how do you,
because it's the closest to the nucleus. We said that that equates to the lowest energy. Does that sound familiar
yeah,
from our discussion from last week? Okay.
Is S
S is the circle because it's always a sphere shape. Okay. P gets populated next. Why? It's the next lowest energy.
which one is, what's P is the
P is the figure 8 shape.
Okay.
Okay. Then D gets populated next, but only after all the P's get populated. We'll talk about that.
Where do these electrons come
That was out of control. Okay.
So-
Dominic, go ahead.
If you have an electron, does it have to be on? You have the figure 8 like this. Does it have to be right here? Does it have to be on that line, or can it be?
No. Generally, we said the figure 8. So, Dominic, remember we said this figure 8 is not like a rigid confined area, right? It looks actually more like this, okay? Like this top left one. It's not a defined area. It's more fuzzy, and really the electron can be anywhere within that. Technically, it can be anywhere, but it's most likely within that space.
So what happens when the sphere and the dumbbell overlaps? Are they in like?
That's kind of weird. So don't worry so much about that, because that kind of gets confusing. Yes, they do sort of occupy the same space at the same time, but electrons don't really run into each other because they're not going to, because they're all negatively charged. So yeah, there is some overlap there, but don't worry so much about that. Okay. Alex, go ahead.
So let me get this straight. S is basically every sphere, right?
Yep.
Within the
And
figure.
every time we change color on this picture, when we go up a principal energy level, when we go from, Alex, we go back to this picture, when we go from this spot to this spot to this spot, we add a circle first.
So that means every P is always going to be within the figure 8.
Yeah, I guess.
And then
Yeah.
D, it's always going to be an X shape.
Right. That's hard for me to draw on here, though.
It's
Now I
like
kind of
three-dimensional.
know.
Say again?
It's like three-dimensional.
Yeah, it is three-dimensional.
So now everything just clicked for me.
Okay, good. Elsa, go ahead.
So with all of this, like, what's kind of like the question you would ask us to do?
Okay. So I might ask you something like this, Allison. Okay? I might give you these two electrons, these two green electrons. And I would say, true or false, those green electrons have the same principal quantum number. True.
Is the quantum number is the
Yeah, that's like the big, that's like Allison, that's like Bohr's rungs on his ladder, right? Except they're not rungs. That's here, here, here. Okay? True or false? True or false? Those electrons exist in the same sublevel. False. Because this one exists in which sublevel? S sublevel.
oh, the other one in the B.
P sublevel.
Everything's
Those the S, P, and D. Those are sublevel.
Right. Yes. All right.
So S, P, and D are sublevel.
Yes.
So
Go ahead.
S has
So, like the principal quantum number, that's like what, like on the diagram, like the colors, like red,
Yes.
green.
Yes. Every time I change colors, that's a new principal quantum
So
number.
it's like just three, like one.
Well, in that case, yes. Yeah. Yes. Hey, go ahead.
there's S 1, 2, and 3. Would that mean there's P 1, 2, and 3?
S. Every level has an S sublevel. Okay. But
except
P doesn't start until you get to the second main level. D doesn't start until you get to the third main level. Does that make sense? Okay, that's good.
Can you go back to the slide where you showed the
Does that mean
example
that
of D? Because you had like a really fuzzy, like
You have a picture of it.
no, but it doesn't show. Like,
Oh, it doesn't come up. Okay.
because yeah, like it's yellow.
Does that mean that P is or the figure 8 or whatever? Figure 8 P. Does that mean it would show up in the third?
There is a P. Yes, it shows up in the third level as well, and it shows up in the fourth. P's show up everywhere in 2 and up.
Yeah.
And then D's show up anywhere 3 and up. Go ahead.
Okay, the only thing I'm confused about, you said something about like 2S. Yeah, what is that?
That's how we distinguish the red circle from the green circle. So when I say 2S, 2 is the principal quantum number. So that's n equals 2. Okay? Then S, that tells me what sublevel it's in within that principal energy level. Does that make sense?
So Wait, I get like everything, but I don't. Where would you write 2S?
Hold on. Later today, we're getting there.
Like if you're just classifying like the thing, it would be like N equals 2, L equals 2.
Right, but there's other ways. There are other ways that we do it. There's kind of shorthand. Once you know the pattern, we can shorten the pattern a little bit, so you don't have to be quite as detailed, but still get your message across.
So 2S means like the second principal level, and it's in the S shape.
Yes. Right. Okay. Remember that.
So P is just the H shape.
Yep, P is the figure 8 shape.
That's
Any one is the fifth. Yes.
I like all the figure eights.
Those are all of them together. Yes. We're gonna do that in just a second. Grace, go ahead.
What do we call this? If
Cool.
supposed to be like,
Technically, there is some technically there is some overlap there, Grace. Although, let's not get too caught up in that. Is that okay? Actually, I want to do something first. Okay. Kirsten, go ahead.
What is like the
It looks like the fifth line. It is definitely weird shaped. So here, hold on. Let me draw it for you. Okay. Kirsten, it looks like this. There's like a figure 8 shape, and then there's like a donut around it. Okay, so it kind of, yeah, it's not an X shape like the rest of it. All right, here's what I'm gonna do. I'm gonna pause the recording because I want to do something here in the room that I hope will illustrate this a little better. Okay? So let's pause this. Yes.
I'm back.
All right, coming back. Using the demonstration that we just did, I'm trying to show you the idea that if we go back to this picture, okay, there's a reason why there's one sphere, there's a reason why there are 3 figure 8s, and there's a reason why there are 5 of these d orbitals in that picture. Because what we find out is that in real life, there is only one S sublevel. There are 3 P sublevels within the second main level. Okay? If we go back to our picture, okay, if I take a look at the green, there's this figure 8 right through here. Okay? Let me see if this works without becoming too confusing.
Wait,
Good.
that blue, like the blue guideline, isn't that also a figure 8?
Yes, but it's a figure 8 in which level? In the 3rd level. Yeah. So here, let's do this.
Some of them want N equals 3.
So
This is 1 and L equals 0.
n equals 1, L equals 0. Okay. Oh. N equals 2.
L equals 0.
L equals 0.
So is it only for L?
Also be S equals 2? Or S?
This is n equals 2 and L equals 0 is the equivalent of 2s. Okay? Because that's fine. Now, what? So, okay. N equals 2, L equals 1. Okay.
Where's the electron?
See? It's anywhere within that space.
L equals 2.
Is there only one?
N equals 2,
L equals 1.
L equals 1.
Why did you do L?
No.
Is L equals 1?
This, okay. Oh. Well, let's do this. Oh, good lord. I have to make it solid. Okay, so. Didn't work so high. Okay. N equals 2, L equals 1. Okay. N equals 2, L equals 1. Because this one,
It's still a figure eight, which both sides.
okay, that's pretty much what I'm saying right now. Because this one is different than this one. Does that make sense?
They're the same.
This one is different than this one. And they're both different than this one. Does that make sense?
But do they list the same neighborhood?
Same street, different.
So, what? In the same city. Yes, but I think it was 2, 1, 2. People are gonna cross this thing, you know, okay, yeah, that's right, alright. I know that.
Okay.
I thought this was physical science, not
Yes.
extremely hard.
This is honors physical science. Welcome to having faith.
Why? I don't like this. I've never felt this way.
I know.
I think I'm not.
I care about your education too much.
Yeah, just stop.
Well, what happens when you put them together? You trying to decide. What is like? They're separate, but they're the same.
Alright, so now look, they all move together now. Okay?
So we'll have to do. So.
Okay? I know. Alright, Kirsten, go ahead.
Okay, so you said they were different, but you just wrote down they were the same.
They have the same first two numbers, but if you go back to like one of the first things we wrote down in this packet, how many quantum numbers are there? 4. Okay? We're only halfway done.
Halfway done?
So,
My brain is about to
the next thing that we talk about is the magnetic quantum number. That's actually an M sub L, but a lot of times we'll just use M. Okay?
We still don't.
So for today we'll just use M. Okay? So the magnetic quantum number is symbolized by an M. It says lowercase L. It just depends on what book you read. Let's just use M. Okay?
We have this one.
Wait, but that is even more of details to the actual like sub-level.
Yes.
Oh.
Because, Allison, if we go back here, okay? Hold on. Here. Finish copying this.
It's in 3D.
It's always been in 3D. I'm just drawing it in 2D. I know.
Why? Thank you. This is freshman year.
No.
This is easy. Just kind of listen.
Exactly. Alright, buddy. First copy this down. What? This is M. Does kind of, it does kind of, no, it does look like no, let's call it okay.
Computer quantum
Quantum numbers.
I super Japan at 10:35
Well, in each of those things that I drew,
don't want to exit out.
each P can hold 2. All right. So, yeah, Chris is here, right? That's what this is saying right here. All right, listen, please. Hey, listen. All right. This is a p orbital. This is a p orbital. It's got the figure 8 shape. This is a p orbital. It has the figure 8 shape. Okay? They're both the same color, meaning they're both in the same principal energy level. Okay? Electrons that exist within these p orbitals, they live in the same city. These two, or Kennedy, these two actually live on the same streets because their L values are the same. Okay, but this one lives on a different street. Okay, but on each street, is there only one place where you can live? No, there's a bunch of different places you can live, and that's where the M number comes in. Okay, we have to distinguish this one from this one. Okay? Sam, go ahead.
So L determines what street you're on, and determines what city you live in.
Right, if we keep up with this address idea. Okay? So, here's what we're going to do. Okay? Next. The magnetic quantum number, M, which we just introduced, indicates which orbital the electron is in within each sublevel. So which house do you live on this street? Does that make sense?
Yeah. It's getting more specific.
Yes. Allison, go.
So like when you draw like one of like so any full two, let's say like the green one.
Yep.
So like this is talking about a place inside of that area.
Yes. Allison, all of this whole picture, okay, is all happening inside of this dark ring right here. Well, sorry. This dark ring right there. That's all going on inside of that dark ring.
How about the like the figure 8, the P?
The figure 8 is happening inside of here.
Exactly, but is there a magnetic quantum number or whatever in that too, or only in the like figure?
The magnetic quantum number, what the magnetic quantum number does is the idea that, Allison, okay, first, everybody got this?
A little bit.
Finish writing this down, and then we'll talk, okay?
Each orbital contains a maximum of 3 electrons.
All right, you got this down? Just go ahead.
Like in a motion shape, would there only be like one of them be like one like so it'd be like
No. This is all one p orbital. The whole figure 8 is the p orbital. Okay? So, if we go back to this picture, okay? This is all happening in the same principal energy level. Okay? But there's different sublevels there. But we have to distinguish this one from this one. And that's where the M value comes in. Okay? For the p orbitals, if we go back to this picture, right? How many p orbitals are there? There's 3 p orbitals. Okay? If we go back to this picture, this one runs along which axis? The y-axis. This one runs along the x-axis. The third one runs along the z-axis, which I can't draw for you because which way does it go? It comes out of the board towards you and into the board away from you. Does that make sense? A lot like this picture over here on the right-hand side. Does that make sense? Okay. But we have to distinguish this one from this one from this one, or this one from this one from this one. Okay? That's where the magnetic quantum number comes in. For the p orbitals, how many p-shaped ones were there?
3.
There's 3. So how many different values for m do you have to have?
3.
You got to have 3 different values for m. What we use for p orbitals is we use -1, 0, and 1. Okay? So here, if I go back to this, if I want to, I'm going to move these just a little bit, and you'll see why in a second. I'm going to call this one +1. Why? Doesn't really matter. I just called it +1. I have to just distinguish this one from the other ones. So here, arrow. Come on. Now those are a group. Okay? This one, I'm going to call m equals 0. Why? Because we said there have to be 3 values, right? -1, 0, and +1. It's just by convention the way we distinguish this one from that one. Is there any real significance to that? Not really. We just have to come up with a way to determine this one from this one from this one. It's not so much that it's random. There's actually a reason. It's like your address on the street.
Wait, was the text like that? So
Say again? Kenny, go ahead.
why is the F0? So now the FX is going to have the -1 for M.
It doesn't really matter. The point I'm trying to make here is it doesn't really matter which.
So
It can supposedly recognize my writing, but it does the best that it can, and I apparently hit the wrong part. Come on. Group. Okay. Kenny, it doesn't really matter which one we call +1, which one we call -1, and which one we call 0. Okay? As long as we just call them something different, so we can distinguish this one from that one from that one. Okay? So I'm going to move this down a little bit.
Does it matter?
It doesn't matter which one you call which, but you have to call them something different, Allison, so we can tell this one from that one from that one.
So like on the test, if you asked us, where is it? And we said +1, it was like,
Totally. Yeah. It doesn't matter. Like, so, yeah, Chris, like on something like this, if I ask you, okay, about this electron and this electron, okay, both of them have the same N value.
Yeah.
Because they're both in the second energy level. Both of them have the same L value because they're both in which sublevel? The P sublevel. But they have to have different M values. It doesn't, because they don't live in the same house. It doesn't matter whether I call this one +1 and this one 0, or if I call this one 0 and this one +1, or I could call this one -1 and this one +1, or I could call this one 0 and this one -1, as long as they're different. Okay? Now, if I add the third one on there, which I can't do on this picture, okay, but if I go to this picture, okay, so this, right, N2, L1, M +1. This, N2, L1, M 0. This, N2, L1,
Isn't that one supposed to be on
I thought it said X.
Yeah, M is supposed to be equals 0 because it's on the x-axis.
Matter which one's which. It does, yeah. Yeah, I know it said, yeah, Alex, I know it said that here, okay? Although it really doesn't matter which one you assign which value, okay? I just kind of said this to give you an example.
So
Okay.
like M equals 1 for x or
Right.
negative 1 for
Yeah.
x.
It doesn't necessarily matter which one you call which, because if I just flip my drawing, can you tell which one's which? No. Okay. Alex, go.
Okay, can you go back to the picture that you drew? Yeah, okay.
Okay.
So, how about if, like, you kept the, electron that is, like, right there? Okay, sure, that one.
Okay.
But then you put one that's in n equals 2, but l equals, oh wait, would it be the,
This one?
oh no, yeah, it would be, yeah, like right there would be n equals 2, but l equals 0.
Okay.
Because, right?
Now, yes.
Okay.
So, Allison, in that case, okay, it has an m value.
Yeah.
But how many s's are there?
1.
There's only one. So we don't have one that runs the x-axis, one that runs the y-axis,
Oh,
one.
so it can't just be 1? Or 1? Or, oh, 0.
We just call it 0. Okay? So if L is 0, M automatically has to be 0. Because how many s's are there?
1.
1.
So this, like, 0, negative 1, 1 is only for the p sublevel?
Right. Now, can I take you to the next step?
Yeah.
Okay. When we add the D sublevel, okay? If you look back at your notes, find out what the L value is for the D sublevel. It's 2. Okay? How many D sublevels are in that picture?
5.
There are 5. So we have to distinguish 5 separate D orbitals.
Oh, I was like 1, 2, 3.
No. When L was equal to 1, we went negative 1, 0, 1.
Oh, so
When L is equal to 2, what do you do?
1.
Negative 2, negative 1, 0, 1, 2. That's the M value. Yes.
What if there's like an odd number?
Okay, there's always an odd number. But, okay, now, so let's see if we can take that one step further, okay, off of this picture that's up here now, okay, F. What does it tell you? How many F orbitals are there? 7 complex shapes, okay? So, what is L for the F sublevel? Okay, it's 3. So Kennedy, what are your possible M values? Negative 3, negative 2, negative 1, 0, 1, 2, 3. 7. Negative 3, negative 2, negative 1. There's 7. There's 7 possible values there. Okay? Go ahead. Okay. Don't try to picture it in your mind because it's like, here's it. If you go this, okay, all 5 of these are all on top of each other. Okay? At this point, I'm not going to have you try and picture it. It just gets really complex. Right? This is how the 3 of them fit together. This is how the 3 P sublevels fit together. Okay? The D's are on top of, there's 5 of them on top of these 3. Don't worry. Okay? Don't try to picture them. Okay? All right. We're almost there, everybody. Almost there.
Almost.
Okay? Now, before you wrote down when we were talking about M, that each orbital contains a maximum of 2 electrons. Okay? If I go to this picture, okay, dark blue running along what is labeled as the y-axis of this picture. Okay? I've got 1 electron here. I can have another electron right there. Okay? So, if we go through the quantum numbers for this one, its N value is still equal to 2. its L value still equal to 1. Its M value is plus 1. Because which axis is it on? It's still on the y-axis. I called this one positive 1 when it was on the y-axis. So I have to call this one positive 1 on the y-axis. These electrons live in the same city, on the same street, in the same house. They're brother and sister. But they're in different rooms. We have to distinguish one room from the other room.
Oh my gosh.
Hold on, just enough to the end. This is it. It's the last slide. Look, and this one's the easiest one. All right? So, the last one, the spin quantum number. All right, let me finish this up here. So the spin quantum number, symbolized by, this is M sub f, let's just call it S. Okay? So we have N, L, M, and S. Those are our four quantum. It's M sub S, so let's just call it S. Okay?
Wait, what's your first L, S?
N, here, Allison. N, L, M, and now,
Oh, like all the things that we.
right. Okay. So the S value tells you the room that that electron lives in the house. If you want, just you can. Actually, what I'll do is I'll post all my drawings. I'll post them online so if you guys want to look at them. All right. Each orbital can only hold 2 electrons. We refer to that idea as the Pauli exclusion principle. And we'll introduce the Pauli exclusion principle apparently tomorrow because we're not going to have time to do it today. So, but electrons have different quote-unquote spin to distinguish them. Does that really mean they're spinning opposite directions? Not exactly. But it's the way that we distinguish this electron from that electron. Okay? Spin quantum number, because each orbital can only hold 2 electrons, only has to have how many values? It only has to have 2 values. Okay? Because, if we go back here, these are the only 2 electrons that can exist in that orbital. So we only have to distinguish this one from this one. Okay? So the S value only has 2 possible values. We call it plus 1/2 or minus 1/2. That's the only possibility. Okay? Here, hold on one second. Let me finish this up and then you can ask your question. Okay. Okay, are we good there? So, we got up and did this. So here, right? This electron, I say, has an S value of plus 1/2. So, why that one? Because that's the one I chose. It doesn't matter. But if this one is plus 1/2, minus 1/2 has to be minus 1/2. What? Okay. Go ahead. Okay. Like this one? Okay. Good one. Hey, this is a good question. Hey, listen. The Miriam asked, what about like this one? Okay. So we have N, L, and M values. Okay. I can give this an S value. Does it matter which S value I give it right now? No, it really doesn't. Okay. I call this one plus 1/2. But now, if I have an electron that ends up here, okay, when you only have 1 electron in that orbital, it really doesn't matter whether you call it plus 1/2 or minus 1/2. What really becomes important is now when there's 2, 1 has to be plus 1/2 and 1 has to be minus 1/2. It doesn't really matter which one's which. Because we have to distinguish, if you go back to the one of the very first things that we wrote down, okay? Each electron has 4 quantum numbers, and they're a different combination for every electron. We're basically accounting for every electron. For the most, they have to all be different. Just like if you have these electrons, these two electrons right here, they live in the same city, on the same street, in the same house, same city, same street, same house, but different bedrooms.
Oh.
Does that make sense? And that's how we identify electrons.
It's a lot, but it all works.
Good. Nick, go ahead.
Alright, so
Come on, hey, people have questions.
let's
so-
say that like on the second level there's
Yep.
two p orbitals.
Yep.
And then on the third level there's also two p orbitals. How
Okay.
would that fit together?
Technically, how many p orbitals are there? How many p orbitals are there always?
Three?
There's always 3. Okay? So now, this picture that we're looking at right now happens in the second level, but then it also happens again in the third level, so a little bit farther out. These balloons are bigger.
But then like with the second level ones be inside the
Yes, the second level ones are inside, kind of like those little like Russian dolls that all fit inside of one another. Okay, that's what's going on here. But it goes here, then here, then here, then here, then here. Okay, here's go ahead.
So the N represents like which kind of like which shape is like which like
The N. Here's if we go all the way back here.
no, the N.
M. M represents actually L represents more what shape it is.
But then
M. But
represents like which shape out of that shape.
right. Which of those shapes are we talking about? If you have an L value of 1, it's a figure 8. It's a p orbital. But which p orbital is it? That's where the M value comes in. Okay. Allison, go ahead. Listen, hey.
Okay, with the N, I know that they have to be the same orbital thing, like you know what I'm talking about?
No.
Like the same
Shape?
one, yeah.
Okay. So if they're the same shape, this value, the L value has to be the same.
Okay, so like I get it. X1 opposite. Like if that light is 1
Yep.
plus 1, then
Or this one. This one? Allison, I see these as dark blue, light blue, and like white. Okay?
And then but like there's not enough like M equals 0, M equals 1.
Because how many of these p orbitals are there? How many p orbitals are there? There's only 3. Okay? So that means
Oh, so then the dark blue, that's 1.
that's 1 p orbital.
Oh, and then that's gonna be.
This is the second p orbital. This is the third p orbital. The whole figure 8 is 1 orbital. So how many figure 8s are in that picture? There's 3 figure 8s in that picture. That means there's 3 orbitals in that picture.
And then like 2 of them would be the same thing.
These 2 are the same orbital.
Yeah.
Those 2 electrons exist in the same orbital. That's why they have the same M value. Okay?
Yeah.
Because that tells you which of the p orbitals are you in. Grace, go ahead.
Can there be like 10 orbitals?
No. As here, Grace, when we go this, there's always 1 s orbital, 3 p orbitals, 5 d orbitals, and 7 f orbitals. Well, it depends on how many electrons there are, right? When you're talking about like carbon, it only has 6 electrons. We don't get that high. So we'll actually deal with that a little bit more tomorrow when we talk about electric.
Not in here tomorrow.
Alright, hold on. Wait. So, for tonight, the sheet I gave you yesterday that said, I think it says quantum numbers homework.
Yeah.
Okay? You should be able to do that now. Alright? Might be a little tough. I will post these pictures online as PDFs. There might be a couple. Are they hard questions? Yeah, they're hard questions. Are there going to be some questions like, hey, what shape is a p orbital?
The orbital is a figure eight.
Figure eight. Okay.
3-dimensional figure.
It has
Which number? This? M distinguishes any which of these. So, there's like these balls, one, fewer.